Last week, we came up to this point, deadbeat control. So today we're going to look at it. This includes most of the things we studied so far, right? Uh, and this is uh, state of the art digital control technique. All right. Okay. So you will see why we call it deadbeat and all as we go. Now, if you look at the control system on screen, right? There you see um, a controller CZ in discrete form, right? And PZ, a plant in discrete form, right? All right. So now these are not coming from heavens or coming from nowhere, right? You know how a controller can be synthesized in discrete format because we did that discrete or digital redesign, right? Suppose you have a continuous time controller. Now you know how to discretize it, okay? How to get from CS to CZ. And also if you have the plant and you have learned how to model a plant, various modeling techniques, right? White box, black box, gray box methods, right? And to get to continuous time transfer function in Laplace. And then you can convert it, redesign it using zero the whole equivalent to the discrete format. So this is a story. It's a long story, but it's a story, right? You have specific chapters, and if you remember all these chapters in that sequence, how they are connected, you can go any long, right? Any distance in that process. One of the problems most of the control engineers are facing is that the story is not continuous, and they have certain steps missing, and they have not connected the content in the proper order. So that is a problem. Otherwise, the story is very clear. Now, we always can't go back to the fundamentals every time you have a problem to solve, right? So therefore, we assume that excuse me, uh, you have some of these things already. You can recall your memory, how you get there. Now, um, now as I said here, PZ is probably a zero the whole equivalent of PS. There can be other discrete versions, right, of a continuous time plant. This is just one. Now, I want to ask you something. Okay, let's say you combine these two blocks together, because once you have controller and the plant both mathematically described and you have connected them in cascade, and then you have the feedback loop, you know how to algebraically solve the negative feedback loop and synthesize the whole thing, multiple blocks in feedback configuration into one single block. This is block diagram synthesis, okay? Eventually to get to one block, let's call it MEZ. So I want you to think like intuitively, right? Don't try to think mathematically, the theories and all that. So think as you feel it, right? So you have an input here and you have an output here, and there's a block in the middle. And what you're doing is you're trying to control the plant. So what do you mean by controlling the plant? When you say I want to control a plant, I really mean that I want the plant to behave exactly as I instructed it to behave, right? Then I have a very good controller. The whole purpose of the controller is to implement my command and generate the output exactly or very close as possible to the command. Okay. So let's say I have an ideal controller, right? Which means when I ask something, it gives it back to me. Let's say a temperature control system, let's say an air conditioner. I just ask, I want 25. And in a while, it gives me 25. And then I ask 24. In a while, in a short while, it gives me back 24. So that is the ideal controller. Okay. This is what everybody is after, right? when they design control systems. Now, if you assume that we have that kind of control system, the CZ, we still don't know how to design it. We assume that we have something like that, so that when you ask the system, this is what I want, it immediately gives you that at the output. Okay. So this is a mathematical technique. If you want to find out something, right, you set the expected outcome on one hand and the reference on the other hand, and try to solve it and see what you should have in the middle, okay, in order to satisfy these requirements. So here also we take the same approach. You have the input, you have the output, and we say output is equal to the input, okay, because it's my objective, with one little difference. When I ask the control system, this is what I want, it gives that to me after one sampling interval. So that's reasonable, right? There's no way, these are all cautious systems, right? So the system has to go through a certain process before it can deliver the expected outcome. So I give one sampling interval for the system. So within that sampling interval, it does whatever required and produce the next sampling interval when I wake up and see that's there. Okay. So I constrain the plant that way, okay, that behavior. So that is the ideal response I should get from a discrete control system. Okay. So can somebody tell me then what is the best possible MEZ? This one. What should be MEZ if it behaves as I expected, as I explained right now? What do you think is this block MEZ? What should be there? For any controller, for any controller, any plant, eventually when you simplify the feedback and everything, what should be here for the system to give me exactly what I requested here after one sampling interval? Can somebody guess? You can at least tell me a wrong answer. Why do you have to tell me the correct answers all the time? You can give me a wrong answer. That's fine. Why don't you try?
A sampler, sir?
Sampler. I think you're a bit closer. You're a bit closer. Yeah, that's a good guess. A sampler. But I did not actually expect that answer, but I think it's correct. Like a sampling device. You have R and you sample it. So the result is exactly the same thing. I want bit simplified version of that, if you will. Now, RK, remember this. If I tell you why your answer is not perfect or in a way not acceptable, if you look at what's on the left-hand side, it's already sampled version, RK. And you don't need another sampler, right, on top of already sampled signal, right? So mathematically, what is it in the middle? It's a one-word thing, like sampler. What is it? This thinking time is important. That's why I have no rush to tell you the answer, right? I want you to think. Oh, I have some activities on the chat. Let's look at that. No transient responses. should be there in between. Right? That's also a correct answer. No transient response. Then what should be there? So rather than telling what should not be there, can you tell me what should be there? Hmm? Hmm. Give it a try. Keep thinking. So the response should be right, very similar or exactly RK, but after a one time delay, isn't it? Because the system takes one time delay to process it, to actuate the drivers and all these things, right? And of course, there is some transients, right? Even though we don't want to see it, it happens between the steps. Okay. By the time you wake up and see, transients have all died out, and you see the level there, right? That is which is equal to RK. So what? What should be MZ? MZ is equal to Z to the minus 1. Now, I'm sure many of you will say, oh, yeah, I knew it, right? Yeah, why didn't you tell me? It's Z to the minus 1. Z to the minus 1 is a delay. Z to the minus 2 is two-step delay. Z to the minus 3, three-step delay. You know that, right? Just a delay. You want exactly RK to be on the right-hand side, the output side, with this only difference, time delay, one-step time delay. So when you have this whole thing, right, equals to Z to the minus 1, you have a perfect discrete control system. Is it clear to everybody?
Yes, sir.
Okay. So assuming that, we can write this equation y z, right? That's the output y z is equal to z to the minus 1 times rk, or rz in z world. Okay. If I write the same thing in time domain, yk is equal to rk minus 1. Okay. Whatever the input at one time step the go, right, will appear here on the output side as yk, right? So you can write it in time domain or frequency domain, right? Z domain, discrete version. Right. So now we have constrained or clamped the system to the best possible scenario, and then we'll go ahead and figure out what CZ should be, right, in order to satisfy this requirement. So this is coming from a closed loop negative feedback system. And for that, if you see the forward loop transfer function and the feedback like this, you can write down what MEZ is for a given CZ and PZ, right? And that is this one. You have seen this in the first semester. The open loop transfer function or forward path over 1 plus forward path, right? That is MEZ. Now we know that it should be equal to Z to the minus 1. All right. Now you can solve this one and figure out what CS should be, right? CS is equal to MEZ over PZ 1 minus MEZ, right? And MEZ is Z to the minus 1. Put it over here and here, right? MEZ equals Z to the minus 1. Then controller is 1 over PZ, 1 over Z minus 1. So very simple, right? This much simpler than what we were doing in continuous time plants or continuous time control development. What do you think? This is just few lines of mathematics, right? You're not hard mathematics. You suddenly get your CZ. This is now more aligned with the data science rather than with dynamics or plant transfer functions or whatever. The authentic, genuine control system design, right, is not what you see over here. You have some sort of mathematical manipulation using discrete data. This is a data-driven approach or data science approach to control systems. Okay, so gradually we are moving from traditional or classical to this data science-based or reinforcement learning, machine learning kind of thing. There we don't really look at the dynamics, right? We don't really want to see the dynamics and get in trapped in dynamics. Because dynamics is complicated, right? The friction, the gravity, gearboxes, bells, pulleys. You can't model each and every one, right? So then your equations becomes very ugly and complicated. And sometimes you might say enough is enough, right? It's not worth it anymore. So let's work on the periphery, right? You have some input, you get an output, and we don't really want to see what's inside, and we try to figure out all these things using numbers, right? So if you have very sophisticated hardware to collect a lot of data and process them in a very complicated manner using neural networks or hidden networks, you don't actually know what's happening, but you get some sort of useful result. Okay, now you see gradually the world is moving in that direction. Right. So we have a controller, CZ. Okay, it's just this. Now, what is PZ? PZ is the Z transform of PS. And if you stick to the zero the whole technique, right? PZ is equal to 1 minus Z to the minus 1 Z transform of PS over S. That's also doable, right? You get the transfer function of the plant divided by S and then convert into equivalent Z format. And in front of that, 1 minus Z to the minus 1. You get PZ. And remember, when you continue this process, and if you get a result, it will be a Z transform or Z transfer function or Z expression, everything in Z world, right? And if you have anything in Z world, a polynomial, right, you can convert it back to time domain, which is a difference equation. So when you have a difference equation, you know how to calculate the samples every time k. This is exactly what you want when you want to control a plant, right? You have a computer or a micro control system or single board computer, whatever it is, which will run this polynomial, right? Or difference equation rather, and calculate every step the control signal. And then you put it into the actuator. Okay, right. So let's look at a classical example, right? There's nothing more important than solving a good example, right, to understand anything. So this is one of those examples, not very complicated, but it has a bit of everything, right, that you need to know. So what is it? It's a satellite orientation control, right? And we are going to do a bang control, right, or deadbeat. So this is the satellites, right? You can see the nice cartoon, and there are gas thrusters on the body of the satellite, and you see the solar panels over there. They're symmetric because you want to have the inertia on the main principal axis, right? So when you give it a little torque using these thrusters, it swings, right, like that. So we want to first write down, first step is plant modeling, right? So we want to model the plant. Plant model is very simple. The torque is equal to inertia times angular acceleration. You know that, right? Any rotation, right? You need to figure out the rotational inertia. The J is rotational inertia times angular acceleration, theta double dot. Okay, theta is the angle orientation. And then you convert it to Laplace world. Tau becomes tau s in Laplace. J is a constant. Theta double dot in Laplace domain is s square theta s, and minus initial conditions, s times theta 0 minus theta 0 dash, okay, rate of change, speed, angular speed at time 0. But let's assume there is all initial conditions are 0, right? So just get rid of that. So this is the Laplace version of the plant model, right? Uh, and if you want to get the transfer function, you want to get a theta s over tau s, output over input, response over reference, right? The reference here, you can develop transfer functions the way you want, right? Sometimes the input is reference, sometimes the input is control signal, right? Depending on what you want. Here, there is no reference. This is the open loop transfer function, in other words, okay? Which means you have the satellite, you give it a torque or thrust becomes a torque here, right? And then the satellite swings. So the torque is the control signal. It's not the reference, right? Reference is if the satellite moves, the reference turns, the reference is actually the angle, the heading. Here, the torque is not a heading. Torque is just actuator signal, right? Some control signal. It's not the reference input. So theta, that is the response over torque, right, is the open loop transfer function, right? Open loop transfer function of the plant, of the satellite. So it tells you what happens when you give a certain amount of torque. That's it. So theta over tau is 1 over j times 1 over s square. So when you see 1 over s square, you see 1 over s is integration. So you have double integrator here. It's a double integrator. So that is the first step, right? Plant modeling. This is extremely important when you venture into various domains, right? As a control systems engineer, let's say you are really good in control systems, let's say, but you know only certain things about different domains. So when you work in different domains, you need to collaborate with domain experts, right? So you bring the control systems, and the domain experts bring the domain specific knowledge, and then you can find a solution. So that's how you solve problems, right? Uh, right. So if there's anything else in the plant when it comes to that specific domain, satellite orientation control problem, right? It's not just control. There can be other things that you need to satisfy in the same time. So you have to keep that also, right, as important issues. But we are not going to look at that direction. Right? This is for some advice only. Then as control designer, right, you move on to plant modeling next. Step 2 is plant modeling. So what is in there? So we convert this plant, which is the continuous time uh, S domain or Laplace domain transfer function, right, into discrete domain, right? We want to design a digital controller for this one, or discrete time controller. So we use the zero order pole equivalent of PS, which is 1 minus Z to the minus 1 Z transform of PS over S. Okay. So let's substitute for this 1 minus Z to the minus 1 Z transformation of PS over S. So PS is here, over S means this 1 over S square becomes 1 over S to the 3, right? It's a triple integrator now. So most of these things are over, including 1 over j, we can take it out. So we are fine with that. So already in the Z world. Now we have some process here. What is the Z transform of 1 over s to the 3? 1 over s to the 3, right? So for that, let's look at the Z table, right? So let's get to the Z table. Do I have it here? So no, should be yeah. Now this is the table where you have Laplace and Z and time, 3 columns, right? Same thing in time domain, in Laplace domain, and Z domain. So we are looking for something like this, 1 over s to the 3. You can see it over here. In fact, this is 2 over s to the 3. It doesn't mind. Um, uh, so in time domain is t square, right? And in the Z world, it is sampling time square z plus 1 over z minus 1 to the 3. All right. So this is what we were looking for, right? And of course, you have to adjust for this 2 because we don't have 2 in our expression. It's 1. So therefore, you have to divide this by 2. So t square by 2. And remember this thing. Is that clear? So this is how you do. Now, if you want to, if you, in the process, you want to transfer your transfer function from S to Z. So you need to use this table. Fine. So now we go back to our problem here. So there you can see t square over 2, right, coming from the table. The rest is here. So once you put it in a nice looking manner, so you can see what you multiply the whole thing by z square, I think, right? This part, right? So this becomes z plus 1 over z minus 1 square, right? And this part is 1 over z. So then it goes here, z minus 1 over z. Z cancel out. So you get to this one. So this is the Z transform of the plant, right? The first part is modeling the plant. Second part is discretization of the plant, right? I'm taking you through these steps because it is extremely important that you understand what is the first step, what is the second, and so on, right? Because when you learn, when I teach, we take little blocks and teach, and if you do not know how to stitch them together, you don't get too far, right? So that's why I'm taking this entire process, not just focusing on the bang bang or deadbeat control, but entire process. Okay. Third step, let's do plant simulation, right? And in discrete time, right? So you have the controller, right? And the plant, right? So remember this one, right? Deadbeat controller is this. Maybe you can write it down somewhere, right? CZ is this one. For any plant, this is the deadbeat controller. Now we know it, okay? And this is the plant, and we have the plant model in discrete time also. Now, once you put your plant model over here, you get the CZ controller, right, entirely in Z domain, right? So therefore, we know this one. We know this one as well, and you can simulate the plant if you wish. And we can write it like this. What about this? Sorry about my nasty writing here. This is theta over tau, right? Theta over tau. Uh, uh, it is the plant PZ, and we have derived this transfer function just a while ago. So we know this block, and you can write it, expand it like that: Z plus 1 over Z square minus 2Z plus 1, right? And then you cross multiply, and theta Z times the denominator here is equal to T square over 2J, right? And Z plus 1 times tau S, right? The tau goes to the right hand side, and theta remains on the left hand side, right? So after that, you multiply the whole thing left and right hand sides with Z to the minus 2 to make Z to the power, right? The powers of Z being negative. You can write transfer functions with Z to the positive powers or Z to the negative powers. But what does really mean by Z to the positive powers is time advance. What is Z to the minus powers? Time delay. So we are more aligned with time delay, right, than time advance. So therefore, we prefer to write it like Z to the minus powers, right? But mathematically, that's same. So then it will turn into this shape, right? And you now expand on the left-hand side. You have theta Z, and then 2Z to the minus 1 theta Z, and then Z to the minus 2 theta Z, right? Now you know these are different samples of theta in time domain, right? In the Z world, it's one expression, but in the time domain, there are different samples. The first one, theta Z, is theta K, the present theta, the heading of the satellite, right? Present heading. And the second term here is theta Z, but in front of that you have Z to the minus 1, which means in time domain, this is the heading just a while ago, the last time. Okay, because you're looking at the process in steps, now and after some time, and after another time interval, right? So it goes like that. So theta K minus 1 is the previous time you looked at the system. What was the heading? Theta K minus 2 means 2 steps back. So you get, depending on your transfer function, you get this expression, how many past samples are there, right? So they're naturally coming from the transfer function. When you write down the dynamics of the plant, right, you're actually writing how many samples, right, that is required in the discrete version. On the right-hand side also, you have Tz with Z to the minus 1 as well as Z to the minus 2, which means the first one is the torque a while ago, one step ago, and then the second one is Z to the minus 2 means the torque 2 steps ago. Okay. So now if you want to calculate theta K, right, this is a simulation, right? You can take the other two terms on the left-hand side to the right-hand side, and what you have is a very nice difference equation, right? It's a difference equation. You start with your position, theta K minus 2, I set it to 0, theta K minus 1, set it to 0, and tau K minus 2 set it to 0. Let's say these are all past things and we don't know what these values are, and we are yet to start the system simulation. So all past things, right? That is anything time negative, you can set it to 0. So what you are left with is only theta k, right? So theta k is 0 because this is 0, this is 0, this is 0, this is, the whole thing is 0. So that is your first step, like theta 0 is 0. And then you go to the second step with some torque, because in the simulation, if you want to see any motion, you have to give some torque. So you produce some torque, right? In the simulation, you can produce arbitrarily some torque, and you can put it over here, right? Tk minus 1, Tk minus 2, like that, right? Then you substitute the other things, mostly 0, but you get something out of that for theta k as you go. Then theta 0, theta 1, theta 2, theta 3, theta 4. When you go like that, you will see some dynamics. Now it is moving because we have given some torque. And that is the simulation, right? You can write a simple simulation and test it for yourself, what's happening. But you have to give an input. Okay, so this is basically open loop simulation. You give a torque and the system will respond to that by turning the satellite. Okay, when you change the torque, it changes. When you reverse the torque, it starts decelerating if it is already moving in one direction, and then slow down and then turn the other way around. Right. So that is the simulation. But what we really want here is not the simulation, but we want to control. Okay, we want to control. Right. Any questions so far? Is everything all right? And you are following well?
Yes, sir. We are following.
Okay. Then we move on to the next step, plant control, the most important part, right? We call the deadbeat controller, which is this one. We derived this earlier. Deadbeat controller is 1 over pz, 1 over z minus 1. When you have this controller, your output will be just the input, but with a one-step time delay. So you can see it over here. You have some sort of uh, error going on to the controller, and the controller will produce a torque, right? And torque goes to the plant, and plant will generate something. Okay, this is how it works. But when you reduce it to the one single block diagram, right, it will behave like this. Like you have input, reference input, z to the minus 1 block, and the output, right? So this is the controller we want to implement. Now we know P is it. We have already derived it earlier, right? If you see, this is PS. In the controller, this is 1 over PS. You can see some sort of inversion here, right? If this is 1 over 3, once you invert it, it becomes 3, or 3 and 3 cancel out. So that's basic principle of deadbeat. You want to cancel all the dynamics like inverse dynamic controller. Okay, you have some dynamics in the plant, you have the exact inverse on the controller side, so they cancel each other. So input transfers to the output without any problem. Right. So this is 1 over PZ, whole thing will flip upside down, right? So we have the control here, 2j over t square, Z minus 1 over Z plus 1. And again, now here we raise it to be convert to the minus powers of z. So this becomes 1 minus z to the minus 1. This becomes 1 plus z to the minus 1. Okay. Now we take inverse z. Okay, to get to the difference equation, similar to what we did with the plant dynamics, right? We developed the difference equation. So when you give a torque signal, you can see how the angle changes, heading changes, right? Now this is the same process for the controller. Right. So in this line, you can see it is 1 plus z to the minus 1 times the torque. Right. And this is the error which goes to the right hand side. 1 minus z to the minus 1 times error. So in time domain, this is tau k plus tau k minus 1, the z due to the z to the minus 1. Okay. On the right hand side, you have the error minus the previous error. So once you take the torque here and move the previous torque to the right hand side, you have a torque equation. So these are recursive equations, because every time you have the difference equation, you will see when you want to calculate, say, torque at the moment, the previous torque is also part of the equation, and that's on the right hand side, right here. Plant is also the same. If you look at when you simulate the plant, right there, you saw when you want to calculate the angle right now, right, the previous angle and the previous angle, right, heading, they're also part of the equation. All right. So now this is the torque equation. So it's very easy to program this torque equation onto a microcontroller and then generate the torque signal, right, every time step and send it to the thruster. You have a deadbeat controller. Okay. So now you can put the whole thing together, the controller and the plant, in discrete time, and this is what you get. Right? You will see the controller here, and you will see the plant here, and you see some sort of inversion, okay. Once you cancel these things out, the result is the whole thing, not just this one, the whole thing is just z to the minus 1, right? And you can see it over here. If you multiply these two together, the result is 1 over z minus 1. And once you put it in the feedback loop, it is z to the minus 1. Pretty clear. In fact, we clamped the system to this state and then did the reverse calculation and design and found controller. So therefore, this is an obvious result. Okay, it has to be like that. Now, if you want to simulate the entire control system, the deadbeat control of the satellite, okay, let's say we put over here the reference input. Now we are putting the reference input, okay, not the torque or anything, reference input, and let's say we put it to 1. So rk is equal to 1, which means every k, r0, r1, r2, r3, r4, right? So they're all ones. They're all ones, okay. Now, because this is deadbeat control, I can immediately say, okay, if that is the case, then from k equals 0, k equals 1, initially there's an error. Initially, theta is 0, let's say. And there's a reference signal saying that this has to be moved to 1. So the reference here is 1, but the response is 0 initially at time 0. Then it's like this. Rk is 1, theta is 0. Okay. But what happens next moment? Next moment, the response will move up to 1. That is deadbeat. After one time sample, step, there's no error. And when k equals 2, It's like that. K equals 3, it's like that. Because Rk is kept 1, and after one time step, it transfers to the output side. So as long as Rk is there at 1, theta k will also be there at 1. Okay. The difference is only one time step. And you can actually see it. It is only visible at time 0. After that, it's not visible. So when you wake up and see what is the orientation of the satellite, it's always 1. It doesn't mean that it stays there all time, right? When you wake up and see, it's 1. But when you are not looking at it, it might change. Okay. So now if we get going with this one, Rk equals 1, and put it into the equation, torque equation. I think it's over here. Yeah. So put Rk, Ek, that is error, initially is 1, and all these things are 0. Torque k minus 1 times 0, right? At time 0, the previous torque is 0. We don't know anything about it. Error, previous error, we don't know anything about it. It's also 0. Anything we don't know, we set it to 0, right? But at present, time 0 is 0 is 1. This is 1. Because you have Rk, you have theta k. This is 1, this is 0. So error is 1. So therefore, your torque at time 0 is 2j over t square. That is tau 0. Tau 0 is equal to 2j over t square. So you can see it over here. Tau 0 is 2j over t square. So when you put that torque, the satellite starts to turn. Okay. Now after one time step, it goes to exactly 1, and there's no error now. Now you calculate, okay, what is the torque should I be giving now? This is the equation which calculates the torque. Now when time is 1, k equals 1, there's no error because now they are equal. Reference and response are equal. So this is 0. But what about this one? This is the error one step ago. Initially, it was 1. Is that clear to you? At time 0, there was an error, 1. Now it is over here. And present error, there's no error. Okay. So this is minus 1. This is minus 1. Right? So then what about tk minus 1? Tk minus 1, because when k equals 0, hold on, go back and see it. When time equals 0, initially theta 0, right? That's where we started the whole thing with the initial settings to 0, right? Error is 1, right? And therefore, error is 1, and previous errors are we don't consider, and then the result is 2j over t square. That's fine. But when the next step comes in, right? Error is 0, right? Error is 0. But the previous error was 1, right? 1. So then this is minus 2j over t square, minus 2j over t square, minus this one, the previous error. Okay, that is also minus. So this should be 2 times. Sorry about that. Sorry, 4 times. Okay. At time equals 1, you get negative 4 times j over t square. All right. You can see it over here in the simulation. You have some control signal initially, time 0, but when it goes to time 1, you have the negative torque twice as big as the previous torque. Okay, so I will make that adjustment to -4 here. Keep that in mind, and let's move on to the next time. Time equals 2. So when it comes to time equals 2, what happens? Time equals 2 means again error is 0. There's no error there. What about the previous error? Previous error is also 0, right? Previous error is also 0. So there's nothing here. Because now, once error becomes 0, next time, when you go to next time, also error is 0, right? Error will settle there to 0 every time k, error is 0 now. But what about this one? This is minus tau k minus 1. Previous control signal, but change the sign because of this negative. The previous time, the control signal was, the torque was minus 4 times something. Now it becomes plus 4 times the same thing, right? Plus 4. It is not plus 2, but plus 4. So it swings back to here. For the next one sample interval, step size, it will stay there, plus 4. You can keep going like that. And the next time step, right, tau equals 0, 1, 2, and 3, when k equals 3, it will be negative 4, right? And the next time step, it will be positive. So you will see this kind of control signal. It goes positive ceiling, negative ceiling, positive ceiling, negative ceiling, like that. This is what is called the deadbeat, right? You can see some, when you do that, right? Look at initial case. When you exert a torque and keep it there, right? For one sampling interval, the satellite starts turn like that. And it comes exactly to 1 over here after one sampling interval. So you wake up and see, fantastic. The heading is exactly what you expected. Heading is 1. Okay. So then what you do is you calculate the torque, how you want to adjust the torque. Now error is 0 based on the deadbeat, and you get minus 4 times something, and you set that torque and execute it, and you go to sleep. So because of this negative torque, now this acceleration, which the satellite has already acquired, now it slows down, right? And then it comes to 0 angular speed, and then start moving the other way. Okay, but just in time, when it comes back, right? This is the kind of overshoot. When it comes back after one sampling interval, it comes exactly to 1. Okay, so now you wake up again and you see, oh, satellite is exactly there. You think that it was there, right, for the entire period. that you were not looking at, right? It wasn't the case. It was going through an overshoot, but when you wake up and see, it's there. And then you calculate the torque, and now it becomes like positive torque, and you release that to the actuator and you go to sleep, right? Then what happens to the satellite is that now it is coming back, and this slows down and go to 0 speed and uh, 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 reflect back, right? So like that, undershoot. So every time you wake up and see satellite is doing well, a good guy, but in between he's going here and there, like most of our people, right? When they are being checked, they're very good, but the moment you take the eye off, then now you to be found, right? So like that. So this beat is not seen. If you are the supervisor, when you come and see, there's no motion. It is like a rock, it stays there, right? But there's a beat frequency, and you don't see it, a dead beat. Okay, beat is there, but it's kind of dead. You can't see it. And also another word for this is bang bang control, because you bang bang means you are hitting the top, and after one sampling interval you are hitting the bottom, right, going back and forth. So right, so I want to give you a little lesson assignment. Why don't you try to simulate, right, say this plant 5 over s square plus 2s plus 5, right? Use the same principles, right? I explained to you, and try to simulate this, design a bang bang controller or the deadbeat controller, and then try to simulate the behavior, right? You should be able to get something like this, right? You have some data here, um, uh, how to set your sampling interval. So it's important that you have a very good sampling interval, right? You can try out various things in MATLAB and then find out a better one. Okay, I will write it down and upload to the web so that you can download and start working on that, the deadbeat control. All right. One more thing I want to tell about deadbeat is that if you want to have any control system which is minimum time, okay, I think the answer is deadbeat control. So this is the control system which gives you the fastest response. It doesn't mean it's optimal, but minimum time, right? If you want to get something done in minimum time, this is one approach, right? If you want to go this way, you throttle maximum. And if you want to go the other way, throttle maximum on the other side. Oh, we can understand that, right? The principle. Maybe it's not energy efficient. It's like how racing cars work, right? When they want to turn this way, that way, always they are full throttle, right? Full steering, full throttle. So because in a race, minimum time is what you want, right? So this is another one. Yeah, this is continuous time. This is same thing in discrete time, right? For various sampling intervals. This is 0.5 seconds intervals. This is 1 second interval, right? This 2 second interval. So you give it a try, different sampling intervals, and then try to simulate it. Yeah. So that's about deadbeat. Any questions, please?
Sir, will this system be an energy efficient one? Because it's always work, right?
Yeah,
For
it's not energy efficient. No, it's not the optimum control system, right? But when you say optimum control, usually you say minimum energy. This is not minimum energy, but this is optimal in a different sense, time critical applications. You want to have the fastest time, the shortest time rather, right? So in that case, this is the way to go. Design a deadbeat controller, right? It's not energy efficient anyway, right? Any other questions, please? All right. Then I want to start the next one, but before that, we'll take a little break. Okay. I'll see you after the break.